finish out the one of three major categories. We've talked about what are the two categories of radioactive waste we've talked about, the big ones. Low-level rad waste and high-level rad waste. And we've talked about the classification itself, what it involves, and also we talked in not real specific terms, but in general terms about disposal and the processes that are used for dispositioning those types of waste. We've got one major category left, and that's transuranic. After we finish this, we will go into general processing, and that'll pick up the rest of the learning outcomes that we've not touched. I know some of you were a little concerned that we'd spent the majority of this time on those first two learning outcomes. We have all those other ones. But we have already picked up the 10 CFR 61. We talked about that and the different waste classifications associated with that. And then the rest of it really have to do with general processing questions and volume reduction and things like that. And that's at the tail end of this. And really the learning outcomes provide you the material, not all the technical content, but by reading those learning outcomes you can get a feel for the topics that will be discussed. So we'll go ahead and move on through picking up transuranic. If you had to guess, what would you say transuranic waste involved? Transuranic. Say again?
The heavier elements.
The heavier elements? Heavier than what?
The 88.
Okay, heavier than 88. But heavier than which isotope?
Plutonium. I'd say uranium.
Uranic? A. Beyond uranium. Transuranic. Beyond uranium. So really it's greater than 92 Z number. What can you say, knowing all that you know about all the elements? What can you say about elements that are beyond uranium? What do they have in common? Alpha emitters. That's correct. So really that's what we're looking at. Transuranic waste are the heavier elements that are beyond uranium, beyond 92, and they are typically alpha emitting isotopes. And they're all man-made. We did it. It's our fault. So here's our classification. Transuranic waste is defined as a waste containing alpha-emitting radionuclides, half-life greater than 20 years, atomic number greater than 92, and we have a specific activity limit. Specific activity is greater than 100 nanocuries per gram of waste. 100 nanocuries per gram of waste. The isotopes that are included in this classification are plutonium, neptunium, americium, and californium. As I said earlier, they're all man-made isotopes.
But curium.
Hmm?
You didn't say curium. I didn't know whether that was a typo or what.
Where?
Oh, the isotopes involved?
These wastes include isotopes of plutonium, neptunium, americium, curium, californium. Where's the typo?
You didn't say curium.
Oh, I didn't say curium? I left it off? Okay.
That's why I was asking.
I just read over the top of it. Curium. That's another one. Some exceptions to that definition would be high-level waste. If it's classified as a high-level waste, it can have transuranics in it. But if it's a classified high-level waste, then it's treated as high-level waste versus transuranic. And also, exceptions can be allotted by the Secretary of Energy with concurrence of the EPA administrator. And it's got to meet some isolation requirements that are specified in 40 CFR 191. Just know that there's ability of the director and the secretary to exempt. And also there are some cases on that are exempted by the NRC that are allowed to be exempted in accordance with 10 CFR 61. Those are usually trace amounts of transuranics. Usually don't fall into the category of a large quantity. But again, it's on a case-by-case basis. The NRC would exempt a shipment with some transuranics in it. Where do you suppose this waste came from? Most of it.
Weapons.
Weapons. Yeah. Weapons production, plutonium production. That's part of it, and also the recovering from that weapons production. The reprocessing of spent fuel and waste generated in production of nuclear weapons. And of course, as we said earlier, we don't reprocess civilian fuel in the United States at this point. We had one time done that as a pilot program, and we haven't done it since. So most of it, really all of it, is generated by the Department of Energy in weapons production. And they do have a considerable inventory of TRU, or true waste, at various locations around the country. I've got a map coming up here shortly that'll give you an idea of some of those locations. And of course, one of the locations is right down the road. Now, because of their long life, because of the alpha emission, and typically they are pretty high activity, there has been a concentrated effort in years recent to come up with and manage a disposal plan. We're not really in the process or in the production mode anymore, because we're not having to produce new plutonium for fireworks. And so really what we're talking about is legacy waste. And we've talked, when we're talking about high-level waste, how some of that's being processed. But the DOE has a comprehensive plan for the safe disposition and disposal of true waste that they have. And it is contained in this National True Waste Management Plan. National True Waste Management Plan. And when you get the PowerPoint, you'll be able to go to this. So I'll go ahead and click on it, show you. There it is. Okay. Well, that's just a cover page or a explanation page. But it is indeed a very comprehensive plan. It covers everything. I mean, a whole lot more detail than what we need for the class, but I wanted to provide it so that you can get just a true feel for what goes on as far as managing this. That there is a master plan, that there are specific steps involved. You can see the program being laid out here as far as the national program. And then there's a whole lot of technical stuff that follows after that. As I said, a whole lot deeper than what we want to go for the class, and probably deeper than what most of you want to go to. But if you're interested, it's there. And if nothing else, it'll give you a feel for the plan that is in place to deal with it. And it's encouraging to know that there is a plan, that it's not just there and that we're going to have to live with it. Now, in that plan, they have basically divided true waste into two broad categories. Okay, so within the true waste category, there are these two subcategories. One of them is called contact handled, CH. And it's just what the name implies, that it can be handled by contact. In other words, a person can go up and pick it up and move it. The other one is on the other hand, cannot. And we'll get to that here in a second. Likewise, I've got a PDF here, or actually this is a document that talks about it, that'll take you and explain to you CH True Waste Characterization Plan, how that works. Whether it's CH or RH, which is the second category, really determines whether and how the waste can be processed for disposal. And so there's steps of characterization that each of them have to go through. Certain criteria has got to be met in order for that waste to be sent to the disposal facility. We're going to talk about the disposal facility here in just a second. It's kind of like, if you want to think of it in this term, kind of like Tennessee FR 61 is the license for near-surface land disposal sites. And in order to ship something to that land disposal site, you have to meet the requirements of Tennessee FR 61. Okay? Same basic concept here. In order for Savannah River to ship CH, True Waste, to the disposal facility, there are certain characteristics that it must meet and requirements that have to be satisfied. And that's the same concept. And so what we're talking about there is basically this. It emits no more than 200 millirents per hour at the surface of the disposal container. If it's a 55-gallon drum, then 200 millirent per hour contacts max reading you can have on it. If it's a B25 shipping container, same thing there, 200 millirent per hour contact. It can be handled in metal drums with no further protective measures. In other words, the 200 millirent per hour, otherwise able to handle it, you can handle it like you do other drums, basically, any other drum. You got a drum pallet, or a drum cart, or hand truck. You can run up, pop it under it, and wheel it down the aisle and put it where it needs to go. It can be stored in either wooden crates or 55-gallon drums. And when it's shipped, it has to be shipped in a specific container. And you see the two approved containers here. True Pack 2 or a half pack container. I've got a picture of the True Pack 2 so you can kind of get a feel for what it looks like. But each of these containers can ship up to, I think, 10 or maybe more 55-gallon drums. But they are transport containers, so that it can be transported safely across the highways and meet the DOT requirements. 97% of all the true waste that's shipped is of this type, contact handled. So 97% of all the true waste that's shipped is contact handled, or CH. And you can see this is where it's shipped to. This is the disposal facility called WIP, Waste Isolation Project Pilot, I think is what it stands for. We'll cover this in detail there in a minute. 97% of all the true waste that is shipped there. Okay, here you go. Can you hit the light back there, Nick? There you go. What you're seeing, this is the lid, and somewhere in here is the shell that this goes into. But this is the inner support ring, and each one of these tiers, I think, has 5 drums on it. This goes down inside the shell, and I think these guys must be over here by it. I'm not sure exactly where it is on this picture. This goes down inside, and then the cap is placed on it, and it's welded.
Yeah, you can see the opening.
It's secured. Yeah, this is the closed one here.
And you can see the opening one right behind it.
Oh, right here?
Yes,
Is that what you're talking about? Okay. That must be it. But you can see where that would be a secure shipping container. They can put 2 of these on a flatbed at a time and take them down to WIP. Now, the other category is remote handling. That's just what the name implies. It has to be handled remotely. And the reason is the dose rates. Greater than 200 milligram per hour on contact. It does require special equipment to handle it. If it's remotely handled, it doesn't make sense that you can't do it with just normal equipment. A remote grapple oftentimes is used with it. Installed slings on the container itself so that they can be grappled remotely. And as you might suspect, it has a special container itself too, and that's the RH-72 Bravo container. The remote handled, it says currently not accepted by WIP. That comes and goes with their certification, and it depends on what they got going on. There have been shipments made from Savannah River to WIP using these containers. And so, although it may say that now, that was true when it was put on the slide, but it may be open for it now. And again, got a link here. Takes you to a document that talks about characterization of remote handled transuranic waste for the waste isolation pilot plant, which is WIP. Within this report, and you can get a copy of this, by the way, this is a free publication, and this link is the National Academies Press where you can get it from if you so desire. It's like 855 pages or something like that.
I have a picture of it on Wikipedia from a distance.
But once more, these documents really run them through and make sure that the waste that's being sent to WIP as remote handled meets the certain and specific characterizations for WIP to be able to accept it. And WIP, as you'll find out, is licensed, much like 10 CFR 61 license burial sites. WIP is also licensed, but it's licensed by a different authority. Nick, if you would, again. Now you can see this is quite a bit different. This is a single shipping container. These big bells down here on this dumbbell, these are transportation overpacks. The actual container is right here. And the true waste in whatever form, whether it's drums or boxes, is placed within that. It's sealed, and then these overpacks are put on the shipping container itself. The whole thing becomes a container. You can see it's not just any ordinary flatbed. It's specifically designed to cradle this and hold it in place. It's shored. You can see there's no room for it to move. What that is to ensure protection of the contents, even in case of a collision with a train. And there is an existing video out there. You can try to find it later of a test that they did on this particular container being hit by a train doing like 80 miles an hour, and it survived. Not only did it survive, it maintained its integrity totally. I don't think it had any dents in it. The truck was gone, obliterated. The overpacks were damaged, but the container itself maintained its integrity. Now that's the way it's set up to work. Because waste isolation project was a relatively new venture. I say relatively new because it took like 20 years to get the license for this thing put together where it could accept waste. But in the interim, plants, facilities, DOE facilities were still generating this true waste. And they were packaging it as best they could under the current regulations, with the understanding, basically, they were going to keep it on site forever. That was the plan. And so some of the methods used certainly do not meet the standards for a waste isolation project now. And in order to prepare this waste now to where it will meet the characterization requirements for WIP, there's a lot of work's got to be done. And the characterization, I mean, it's pretty specific. It gives, details things concerning structural integrity, what can and can't be in it, and et cetera, et cetera, et cetera. And so what the sites, Savannah River being one of those that was involved with it, had to do was go in and retrieve some of this legacy waste and characterize it. That's some of the waste that they would find. Now, this contaminated is true waste, remember. It's contaminated with alpha, has alpha emitting isotopes all through it. Some of these alpha emitting isotopes are also neutron emitters, the California is. And so you have not only beta, gamma, and alpha to deal with, now you have neutron also to deal with. And because this is some of the stuff that's down in these boxes. And so you can't just go jump into the box and open it up and say, let's see what's there. So they had a pretty good protocol going on out there, as long as they had the money. So I think they've had to shut it down now because of budget constraints. Because it is something you can kind of hit pause on and wait until you have funds and then come back to it again. But they had a process set up where they would take the container, the existing container that it was in, they'd take it and x-ray it. And through that x-raying, they could tell if there were any prohibited item type things in there. Aerosol cans, for example, were not allowed at WIP. Containers of liquid are not allowed at WIP. So you could, through the x-ray, you could kind of detect that. And then the RP techs, what they would do is they'd take their alpha, beta, gamma, neutron survey meters and characterize it that way. Here's some other things. How'd you like to see that? That's 4 55, actually it's sitting on 5 other ones, so there's 9 55-gallon drums in here. And this is the way they packaged it. What they did, you've seen these huge concrete culverts? I mean, you know what a culvert is, right? It's a big concrete pipe. And I'm talking, that's what this is right here. Big concrete pipe. It was not designed for this purpose. But they would take and seal the end off with a cap. And when I'm saying seal, it's probably silicone caulk and stuff, and however else they might seal it. They would stack the drums in there. And then they would put a loose fitting top on it and caulk it up as best they could. And then they set it off in the burial area out there. Not necessarily buried. So over the years, the weather, it'd fill up with water and other assorted things. I'm sure they had some critters in there too. And rust. Well, WIP came along. We've got to disposition this waste. We've got to characterize it, so that means we've got to go in and open all this stuff up. And here are some of the things that they had to open up. This is a recent picture. This is like from less than a year ago. Some of the stuff that they were working on through the True Waste project out there. So once they x-rayed it, figured out what they had, dose rates, then they would open it up and they'd go in and individually, and usually remotely, depending on the dose rates, remove these from these makeshift casks and individually x-ray the containers, dose rate them, and then they would put them inside containment huts with ventilation. Someone with a bubble hood and bubble suit would go in with an RP, and they would open it up and start sorting through it. and taking and segregating the items out. That's the True Waste Project. If you hear someone talking about that, that's what goes on out there. That's some of the challenges. And it's not just at Savannah River, it's like that all over the DOE's facilities. And so they had to be characterized prior to being sent to WIP. And then they would be repackaged in the proper containers, in the proper way, and with all the pedigrees and the documentation saying that it met the criteria before it could be shipped to WIP. Any questions on that? Okay. Around, you can go ahead and turn that back on there. Thank you. Around the United States, you can see the legend over here. The gray is the contact handle. The little red disc, or the remote handle, that's the relative quantity in cubic feet, or cubic meters, I'm sorry. Obviously, Washington has most contact handled. Proportionally speaking, South Carolina has quite a bit remote handle. You can see the numbers down here. Actually, it says 0 for remote handle. Oak Ridge. Oh, I'm sorry, that's Oak Ridge, yes, thank you. Oak Ridge National Lab, 2,254. Whereas Hanford has the most contact handle. This, just for reference, when we start talking about it, that is where WIP is located, southeast corner of New Mexico. Now, distinction is made. These are large quantity sites. There are also, as you can see, numerous small quantity sites, little research laboratories, and things like that, scattered all over the United States with the quantity in cubic meters. Any questions on the classification itself? All right, we've already touched on disposing of it, so let's get into specifically talking about the disposal. The DOE has a manual on radioactive waste disposal, and within it, it sets the standard, if you will, that says that transuranic waste, this is obviously waste that's generated at DOE sites, shall be disposed of in accordance with the requirements of 40 CFR 191, and you can see the title there. 40 CFR is the EPA regulations. The EPA regulations. And so within the DOE, they have made that statement and proclamation that all of their transuranic waste is going to be processed in accordance with EPA regulations. So that is the governing regulation for transuranic waste disposal. Now, as far as general things, and for your purposes, later you can come back. This link takes you to the manual, the document that shows the manual and all the stuff that goes into it. And this also will take you to 40 CFR 191. As far as the standard itself, again, this will take you to the standard to the EPA. But in general terms, here's what that standard tries to achieve as far as transuranic waste disposal. One, long-term isolation of the waste, both quantitative containment requirements and qualitative assurance requirements that it's going to be disposed of in a manner in which the public safety will be maintained and that the minimized impact on the environment. It also includes individual and groundwater protection requirements. That's kind of the principle or philosophy for the standard as far as dealing with transuranic waste. And it is designed and intended to give confidence the desired level of protection is achieved. And whether a specific repository will work or not is determined on the probability of release due to foreseeable natural processes and releases due to human intrusion or unlikely natural events. In other words, it tries to cover all the bases. meeting or I guess specifying the repository requirements. And here's the kicker. Requires quantitative, not qualitative, but quantitative analysis of release from unlikely and unforeseeable natural events for 10,000 years after waste burial. 10,000 years. We can't tell you who's going to win the election tomorrow. But there is a quantitative evaluation that they have done, and as you might imagine, it's enormous. And it does cover, as much as they possibly can, every conceivable event that might lead to the release of radioactive material from this repository. That's the general philosophy. All right. As far as specifics and standards that can be measured on a day in and day out. You can see that it says here that the waste, and it says that the NRC management, in accordance with EPA standards, transuranic waste be conducted in such a manner it provides reasonable assurance that the combined annual dose equivalent, okay, so that's what we're looking at here, combined annual dose equivalent of any member of the general public shall not exceed 25 milligrams to the whole body, 75 milligrams to the thyroid, and 25 milligrams to any other critical organ. Those are the NRC transuranic waste. As stipulated in the EPA standard 40 CFR 191.03. Now, as far as DOE transuranics, same basic opening paragraph, but it shall not exceed 25 milligrams to the whole body, so far that's the same. But then what it does is it just says 75 milligrams to any critical organ. Any critical organ. It doesn't split out the thyroid. Now keep in mind, this is criteria for the disposal site. These are the standards that have to be met in order for that site to be functional or to be allowed to be functional. Now, as I said, there is one site, the Waste Isolation Pilot Project, or plant, that accepts transuranic waste. Southeast Mexico, 26 miles southeast of Carlsbad. We'll show you a map here in a little bit. You can see how close it is to the Texas border. It's just spitting distance. It's right there. It's the nation's first and only geological repository for permanent disposal of true waste and true mixed waste. And we're going to talk a little bit about mixed waste here in a little bit. That's kind of a unique animal in and of itself. But it's the only one. It's just, I guess if you want to look at it, it is a success story in that it shows it can be done. And everybody was kind of pointing to this when we were talking to Yucca Mountain, saying it can be done. And we were that close to Yucca Mountain and been able to have two success stories. This one for true waste, the other for high-level waste. It is part of the National True Waste Management Plan, and again, there's a link here for you to go to the document that contains that plan. But waste isolation, or WIP, is included in that plan. It's only licensed to accept true waste. It can't take high-level or low-level waste or spent nuclear fuel. Only true waste. Here's the location of it. Here's the New Mexico map. WIP is right there. And you can see here's waste isolation site. This is Texas down here. So it's very close to Texas border. But not too far from Carlsbad. And in general, it really is a network of underground excavations or tunnels, working spots, about 2,150 feet. It's embedded in some ancient salt formations. Ancient salt formations. Now the fact that it's that deep and it's in salt makes it ideal, plus the fact that they get basically no water, no rain down there, makes it ideal for radioactive waste storage. Salt flats, you kind of have to think in terms of table salt, but solid. How many of you ever been to a salt formation, a natural salt formation? You know what I'm talking about, right? It's just kind of solid. And you can mine it. I mean, you can chip it up and mine it. But what's neat about salt is that over time it is fluid. It moves. And what makes this such a great deal, a salt bed formation, such a great repository, is that you put your waste in there, and over the years the salt will actually move in and fill the voids and will lock it in place where it's not going anywhere. That's just a natural feature, characteristic of the salt formation. What makes, and this slide here, I'm not going to read it. You can come back and read this. This kind of gives you the history of it, what took so long. It took 20 years to construct it and test it before the EPA finally said that it could be used. It opened in March of 1999, taking the first shipment, and the shipments have been going there basically ever since. It's supposed to have a 35-year life with a 10-year closure window. We're get 10 years to restore it and close it with specific requirements for the closing. I was hoping this would say something about the layers. Yeah, it does here a little bit. So I'm not going to go over history. Just know that 1999 is when it first started receiving shipments. It's basically 4 vertical shafts for ventilation and also access to the operating level. 56 rooms down there, dimensions 300 feet long, 33 feet wide, 13 feet high. That's the chambers in which they put the waste for final resting. Taken waste since '99. Eventually be able to store 850,000 55-gallon drums of waste in there. That's a lot. And as I said, the salt, it's not pure salt, it's bedded salt. By that it means it's in layers of clay, which is even better. Because clay has a characteristic of basically performing a water barrier. And so it will protect the beds. Basically, also the fact that the salt is fluid, any fractures in the salt are pretty much self-healing, that they kind of close back up. And this gives you, go ahead and shut that off, Nick, if you would. Thank you. You can see the 4 shafts and the operating level down here, about 2150 level. Sea level going down here about 3,400 feet. So it's above sea level. Let's give you some idea of the geology associated with it. As far as the number of shipments, this is estimated, and I think this is the estimated total. You can see Savannah River is estimated, I think, to have the largest number of shipments. No, wait, that's Hanford. Hanford, this is Savannah River. Now, Hanford has the largest quantity. As far as decommissioning, there's a 35-year useful life after which it'll be decommissioned. It's really cool. It was designed for decommissioning. Turn that back on there. Thank you. In that everything is coated for ease of decontamination. Cracks and joints were sealed so that contamination couldn't get down into them. All the architectural features of it are designed for dismantlement. Ventilation, removal of equipment, all of that is designed where it can be easily removed and decontaminated. So it was built with decommissioning in mind, which is probably a first of its kind, including ventilation. And it is designed such that decommissioning will maintain doses of LAR. In fact, all of the EPA requirements are geared toward that LAR concept, including the different classifications for the waste. That is all for the sake of the workers on the other end handling this stuff. The characterization as either contact handle or remote handle, so that when a remote handle comes in, they're prepared to handle it, they have equipment in place to handle it, they can unload it with minimal contact, and doses are maintained LAR. So it is truly designed as an LAR facility. The plan includes removal of all the equipment, buildings, closure of the shafts, basically sealing it off, and also implementing some passive institutional controls to the facility, including intrusion prevention. And it's got to remain in place for 10,000 years. Now, the steps that are in place right now have been determined to be adequate for protection over a year's period of 100 years. Okay. They are still researching how to really get out there to that 10,000 year mark. And I think I have a link here somewhere. There's another document that has evaluated some of the possible things, because one of the things they're trying to consider is, will English still be the language? And if it's not, what would be? And can we really, in 10,000 years, can we really say what the language would be? And so it's kind of along the lines of the Voyager, the spacecraft that they put out there. And, they put a little plaque on there to communicate where it came from. And so they used a combination of pictograms, and I think there was even a record, not vinyl, it was made out of metal, but a record with all the languages of the world at that time on it. And but so I mean, they're looking at all that kind of stuff. How could they communicate the hazard in a manner in which someone 10,000 years in the future would be able to understand that it's not a good place to be? You don't want to dig here. This is, there it is, intruder deterrent. If you go click on that, it takes you to a document. This is one idea, that you would erect these monuments. You can see that these are people here, so there'd be a huge monument field over it, and somewhere along in here, yeah, right there. That's a communications cubicle, and in here would be whatever means they come up with to communicate the hazard. You go in there and read about why this monument is here. I mean, think about it. If you saw something like that, you'd want to know, what does it mean? Kind of like Stonehenge, right? Yeah. Maybe that's what Stonehenge is. Don't dig a Stonehenge. That'll give you some idea. Questions on true waste? Okay. Tell you what, let's get through mixed waste and then we'll take our break. Because this is only 5 or 6 slides. All right, we've talked about high-level waste, we've talked about low-level waste, we've talked about true waste. And each of those had specific characteristics that determined that it would fall into that category. Well, there's a fourth, and it's this, mixed hazardous waste. Now, mixed hazardous waste has this feature. It can be any one of those 3 categories that we talked about. It can be true waste, high-level waste, or low-level waste. But it has another component added to it, and that is a hazardous substance, such as biological hazards. Maybe it's the E. coli virus. Okay, a radioactive E. coli virus with alpha greater than 20-year half-life. That would be a mixed hazardous waste. It could be this high-level waste that has chemicals in it, and there's a lot of that. Think about how we process the high-level waste. It was using chemicals. And so you get high-level waste with chemicals mixed in with it, you've got mixed hazardous waste. And likewise, if you do that with true waste, you've got true waste that has chemicals mixed in with it. You have mixed hazardous true waste. And so there's a lot of different ways you can get it. But if it has one of the biological, chemical, and I'm sure there's a third one, I can't remember what it was. We'll come up on it here in a second. But any of that causes this waste now to fall into that fourth category. Because that fourth category, this mixed hazardous waste, requires special handling. Because 10 CFR 61 does not control mixed hazardous waste. None of the burial sites licensed under 10 CFR 61 except one. I think one's licensed by the EPA to take mixed hazardous waste, but the other ones are not. Likewise, WIP has 2 different certifications. One is non-mixed hazardous waste, which is regular true waste, and the other is mixed true waste. So 2 different certifications, and they handle them 2 different ways at the end. So mixed hazardous waste is radioactive waste that also contains non-radioactive hazards such as chemical and biological. The actual definition is contained in this RCRA, the Resource Conservation and Recovery Act. I'm not going to go there. But it is regulated, hazardous waste, mixed hazardous waste, is regulated by the EPA, and it's a cradle-to-grave regulation. They, from the time it's born until the time it's put to bed, the EPA regulates it. Now, this regulation is in harmony with the NRC and the DOE, as well as the agreement states. There's no conflict. It works together. You got the DOE and the NRC are concerned with the radiation safety aspect of it. The APA is concerned with the hazardous waste safety aspect. So the NRC and DOE regulate radiation safety. EPA takes care of regulating the hazardous waste safety. Now, almost all of the commercially generated, and that's the non-DOE, mixed waste is composed of low-level waste and hazardous waste mixed together, and it's given this name, low-level mixed waste. Low-level mixed waste. It is produced in all 50 states, industrial, hospital, nuclear power plant facilities. I've got a breakdown here trying to give you an idea of what comprises of it here in a second. But they're used in a lot of different processes. Medical diagnostic testing, research, pharmaceuticals, technology development, pesticide research, as well as nuclear power plant operations. So Each one of them contributes their own little bit to the pot in generating this commercially generated waste. Now, how much of the total is commercially generated? Less than 2%. So, yeah, we generate some in the commercial sector, but 98% of it's generated or stored by DOE. As far as the commercial, this just gives you an idea of the sources from the industrial, pharmaceutical, seal source manufacturing, and radiator manufacturing, fuel storage fabrication, biotechnology, and all that would contribute to the mixed hazardous nuclear power plants, as well as medical and academic community, hospitals, research reactors, and lab research. Those are the three big players in generating the commercial. The actual breakdown, if you look at it, you'll see almost all of it is this LSC, liquid scintillation counting. Remember when we talked about liquid scintillation counting and you mix this fluor and the chemicals that you put in there and shake it up? Well, those chemicals just made mixed hazardous waste because it's radioactive and you just added chemicals to it. Now, that little vial doesn't sound like much, does it? But you multiply that by the number of times that you do samples at each facility. And this is also done at hospitals because they have to do gamma specs and as well as liquid scintillation counting for energy determinations on some of the radiopharmaceuticals that they use. Research facilities, hospitals, and universities use liquid scintillation. And so you can see almost all of it, or a huge chunk of it, is liquid scintillation waste. And then the rest of it, organics, solutes, and toxic metals, and the famous other. So that's commercial waste. Big thing to take away from that is small amounts contributing to the total. The biggest contributor to it would be the liquid scintillation. As far as DOE, mixed transuranic or MTRU obviously has a hazardous component plus the transuranics. Same criteria, greater than 100 nanocuries per gram, contaminated with the hazardous constituents specified in the RCRA. The principal hazard, of course, is the alpha emission and the internal hazard that it presents. But the hazardous waste is also still there as a hazard. Generally generated during nuclear weapons fabrication, plutonium-bearing reactor fuel, spent fuel reprocessing, all those things we described when we were going through high-level waste reprocessing and using the chemicals and pulling the nitrates out and dissolving the cladding and all that stuff. That's where this came from. About 55% of DOE's true waste is this mixed true waste. So a little bit over half of their true waste is mixed true waste. They had up at Rocky Flats in Colorado, they have remediated 1,500 cubic meter of it, and that's been retrieved and sent to WIP, and that site has been closed. They do dispose of the mixed true waste at WIP under that mixed true certification that WIP has. And again, before, like any other true waste, but now it's mixed true waste, it's got to be properly characterized before it can be sent to the disposal facility, before it can be sent to WIP. And that's what these regulations are that it's talking about here. 40 CFR 194 is the hazardous waste. This is the radioactive aspect of it. This is the hazardous waste aspect of it. Now, DOE owns and operates basically a license, is licensed to operate with by the EPA. There's initial certification that had to be done, that has been achieved, and it has to go through recertification every 5 years in both true waste certification and mixed true waste. I think it says there, yeah, the last recertifications were in 2006 and 2010, so here in a couple of years they'll be up for recertification again. As long as they meet it, no problem, they can keep shipping. If there's a delay in the paperwork or for whatever reason the processes don't satisfy the EPA regulations anymore, they'll pull the cert. You can't ship to it. As soon as they meet certification requirements again, then you can start shipping to it. That's the way that works. This gives you some idea of the major players here as far as the mixed true waste that's in process as mixed true waste. You can see 90-something% of it is from Idaho now. That is not to say that it was all generated in Idaho. Because what DOE did for a while, and they may still be doing it, whenever WIP is not taking it, they go ahead and ship it up to Idaho. And it basically is held up there, waiting to be processed or waiting for WIP to open up again. So a lot of this did not originate in Idaho, but rather someplace else. But it was, you ever been up to Idaho? It looks a whole lot like Nevada and Arizona and New Mexico. Yeah. Especially out the Idaho test site, it's huge, open range. It's high desert is what it's called. Okay, any questions on mixed hazardous waste? Just that fourth classification, keep in mind it is mixed hazardous waste because of the addition of something in addition to the radioactive aspect. And that puts it into that classification. Let's go ahead and take our break. We'll start back up at 20 after, and we will finish this tonight.
He said he tried to do it today, but something that I started that he's going to post it in the class.
Act series starting with 88.
So it sounded like
starts at
today.
88.
Okay, so that one be more.
No, 92. That definition I gave you on the slide is the definition.
But in the same
Homework.
in the same of the book it says it starts with the 88.
It says the Act 9 series starts at 88.
Yeah. So it's 92.
Yeah.
Like it took me a second to know.
This section, we're going to go back and pick up those learning outcomes that have to do with waste processing or volume reduction. And what we've done is taken it and really brought in some general principles. And then we're going to take each of the three big types, the solid, liquid, and the gaseous. And we're going to look at those methods that are used in each of those waste processes, for each of those forms of waste. So we'll start with the general principles. And just as a reminder, as far as this is taken for a power plant, but you can apply it anywhere. As far as the three major types or physical forms, liquid, solid, and gaseous rad waste. And as you kind of use this as when you go back and look at the different methods that we will talk about, we talk about a lot of these and how they fit into the processing. You'll see that there's kind of a crossover between liquid and solid in that in the evaporation process where after you get rid of the water, you actually are generating a solid that has to be processed. And this shows a solidification process as being one of the means for doing that, going into a drum. And also, coming off of this, there's a dewatering step, so you're removing the liquid and feeding it back up into the liquid rad waste system. So there are some kind of crossovers, if you will, between a couple of the types. Not shown here, but the gaseous rad waste, the filter here is to catch any, these two filters catch any particulate, so they're going to generate solid. And these filters are going to have to be processed, and so they would fall back up here in the solid section and be processed as solid waste. So there's a little bit of a cross there. Same way here, liquid waste, going through a filter and then through an ion exchange. And the resin that's used in these ion exchangers has a defined life. And once it's done, it's spent. So this spent resin comes back down through here into a solidification process, and in essence becomes solid rad waste that must be dispositioned. So that kind of picks up, in a general sense, the three forms, and we're going to get a little bit more to that. And if we take and look at the philosophies or the thoughts on how to process waste, you can kind of break it down into these three things: delay and decay, concentrate and contain, or dilute and disperse. And you can see within each of those categories, we've kind of laid where the three major categories fall. Delay and decay is used a whole lot on low-level waste, usually on short-lived isotopes, and for all intents and purposes, that really is talking about medical radionuclides. I'll talk a little bit more about it here in a second, but it doesn't really work real good for rad waste, low-level rad waste in a power plant or even at a DOE facility. Concentrate and contain is the primary one that's done for high-level waste. You'll recall the process we talked about there was after those big tanks were there to hold it up for a while so that the short-lived would decay, but then you have these long-lived isotopes that you have to deal with in high-level waste. And we evaporated the excess water off, concentrated it down to where we had solids, and that's this concentrate step here, and then basically contain it until you can do something with it. In this case, what we were talking about out there that is done, is in the process of being done, is removal of the strontium and the cesium from it, and then processing it on out as salt waste. And then the strontium, cesium, and the other sludge components are taken over and through the vitrification process, where they're evaporated down, concentrated, and then mixed with glass for encapsulation. And then down here, dilute and disperse. That deals really with low-level waste, primarily liquid, and in some cases gaseous. And we'll talk in detail on that here in a second. Three basic principles: delay and decay, concentrate and contain, and then dilute and disperse. Delay and decay, a little bit more about that. It's not always feasible for the larger facilities like DOE and power plants because of the diversity of the mixture of isotopes that we deal with. You have anything from isotopes with a millisecond half-life up to isotopes with several years half-life, all in the same waste stream. So it really doesn't make sense that you would set it aside, let it decay, delay it off, or decay it off. Short-lived, mixed up there. Also the storage space that is required. Most power plants do not have large storage capacities. And so to hold up several 100,000 gallons of water and wait for it to decay off is infeasible. So it's not really a process that's used a lot in power plants. It is very useful in hospitals and research facilities, where most of the isotopes that are being dealt with are pretty short-lived. You have a little bit more availability of space. And so after you clean up a room after an iodine-131 treatment and all the trash that's generated off that, you bag it up, you mark it as iodine waste, and you go put it in a short-lived locker or a warehouse. And in 7 half-lives, which was about 30 days, you go back and survey it, and it's normal trash. You just throw it out in the dumpster. That's where that comes in handy. And just go back to storage facilities again. As far as concentrate and contain, what that involves is reducing the volume of liquid down as much as you can, concentrating the solids. And then you store it safely in a high or in a controlled area. Ultimately, the highly radioactive items will be solidified for long-term storage or long-term disposition, disposal. And normally they are segregated and stored well away from anybody that might be exposed to it. Like we talked about in the large rad waste tanks out at the tank farms. They're buried underground. You can let them sit there for a number of years, which they have, and then process it as funds are available. As far as dilute and disperse, you use air or water to dilute some concentration so that when it is released, it is within the release criteria. If I've got a volume of liquid rad waste to dispose of, and I've got a stream of clean liquid, say my circ water system, that's the water that's used to condense the steam. It's a clean system. And usually, you circulate it, either you're sucking off of a basin at a cooling tower, or you're sucking off a reservoir like they do at BC Summer off the lake. You send it through, and on the discharge end, you've got the discharge of this clean water going out, right? So if I take my volume of radioactive and I release a small amount of it over time in that discharge volume, I have diluted it. My microcuries per cc out here is well within the limits permitted by my license. My total curie content is still there. I mean, I still have a total curie content in this volume here, and my total curie content that winds out there is the same, and that is limited by my tech specs and my license as well. So it is a method, it's an approved method for disposal of liquid rad waste. It's a dilution process. It does require that initial concentration to be low activity. You can't really do real high activity using this method. And by doing this, we minimize the concentration of the radioactive material. Now, that doesn't say that it doesn't wind up in the lake, because it does. But again, your license permits you to dispose of a specific quantity of radioactive material over the course of the operation of the facility. And it's undergoes a lot of scrutiny, a lot of controls, and very strict accountability. Those types of things are addressed in your environmental tech specs and your radiological environmental impact statements or management plan, your RIM. The facilities are designed to be able to do that. I mean, there's installed piping and systems that have specific design features. Those include things like the installed pathway for either liquid into the plant's discharge stream or gaseous into the plant's ventilation. Either way, it's a dilution and dispersion. The release path has installed radiation monitors. They are there to detect and measure the amount of radioactivity that's being discharged. And it usually has some recording device even associated with it. There are established and approved procedures with appropriate level of authority to approve these quantitative releases. Usually it requires for a power plant, it requires the on-shift supervisor, which is the operations supervisor for the plant for that shift. It requires his approval. The release is usually calculated by the cognizant group, which normally is the chemistry group. They're the ones to sample it, quantify it, and make a recommendation on the discharge. There's plant procedures that govern this, but you also have the Environmental Protection Agency or State Department of Health that has a discharge permit that has to be filled out every time a discharge is made. All of this is there to ensure that the quantities released are as prescribed by the tech specs and the environmental tech specs, and they, by design, are there to protect the environment. I mean, that's the purpose of it, the general public and the environment. All of that, including the discharge, the actual microcuries per cc that's discharged, is used in the off-site dose calculations that go into determining whether this hypothetical man that we talked about, the person that lives at site boundary 365 days a year, eats all the food off the land, drinks the water from the river, all that guy. All that's there geared to prove that he didn't receive any more than the dose limit allowed by regulations. So these discharges are calculated into that. Let me just give you the effluent is sampled, isotopic analysis is done, the activity analysis. The release quantity is used to calculate that off-site dose projection, as I just mentioned. It makes use of the DAC values that are published in the regulations for the specific isotopes, which are all geared toward, and if you recall, I think this was on your last test in 243, it's geared toward determining the total effective dose equivalent. Most of the systems have an automatic feature design to where the discharge quantity is entered into the computer and control system for this valve. Input from the radiation monitor goes to the automatic trip feature for this valve. And if radioactivity levels reach a set point, they will automatically secure the discharge. Boom, close it off. So it would stop. And then you'd have to take actions to figure out why it closed off and why it stopped. Any questions on dilute and disperse? Usually get eyebrows raised. I saw Jerry's eyebrows raised and he grinned a little bit. Because there's a little saying in RP land, it's called dilution is the solution. But it is an approved and perfectly legitimate way of disposing of rad waste. It's a design method. As long as you follow all these and use it as an approved release. This would be called a monitored pathway. And it would be a monitored release. Any questions? All right, we're going to take now each of the physical forms and take a look at the methods, if you will, that are used to process them. We're going to start with solids. Now keep in mind there's crossover between the physical forms. These are the main ones: prevention, compaction, incineration, solidification, and vitrification for solid waste. Now I included these, especially the vitrification here. It could very easily have fit down, and it is, I think, listed also on the liquid. We'll only cover it once. In fact, we've already talked a whole lot about it, so we probably won't spend much time on it at all. But I do want to start up there with prevention, because that is the simplest, is the most cost-effective, and in some cases the least used to minimize the volume of rad waste that's generated at any facility. It doesn't matter if it's power or DOE or hospital. One way you can do that, prevention, is removing unnecessary packing material from items being taken into a radiologically controlled area. New parts and such come with a lot of packing material to ensure that it doesn't get damaged during shipment and handling. A lot of that can be removed prior to the item being taken in. If it needs to be protected from damage, then obviously you wouldn't want to damage a delicate part or an expensive part that might have to be replaced. But by and large, you can reduce the volume a lot with this step. You want to segregate non-radioactive waste from radioactive waste prior to disposal. For example, let's say this room's posted a radiologically controlled area, buffer area, and over in this corner of the room, we've got a contaminated area set up. And we've got a step-off pad right here with the receptacles. Got a contaminated trash receptacle and a PC receptacle. Well, if I have some paper out here that I want to dispose of, if I take and toss that in that radioactive receptacle, I've just taken some probably clean stuff and put it in with some stuff that's definitely contaminated. Well, I've just increased the volume. So being sensitive to that, keeping those segregated, disposing of anything out here differently than what you would dispose of what's in there. And don't let this move into that area there. That's what that's referring to. Use of launderable items versus disposable items where it's cost effective. Big illustration I give you is, and you've experienced it every time you dressed out, the use of tape versus the use of those sleeves. Those cuffs that you use, those are launderable. They can be reused. They're sent off to Unitech, cleaned up, and sent back and used again. Tape, on the other hand, goes in that contaminated trash barrel and becomes radioactive waste. That's a good example. Power facilities have even gone to the point where they don't use paper to clean up wet. They use launderable rags. If you have a spill or you've got cleanup to do, you'd use a rag versus using paper products. Now, and the reason I added this cost-effective bit here, there are some special PCs, protective clothing, coveralls and such, that are disposable. But they're special. They're the Orex. Have y'all talked about that at all? The Orex. I'm looking for somebody's indication here. Yes or no?
Just mentioned it a million times.
Probably heard it.
That's about it.
A lot of plants use those instead of the coveralls like what we have. And the reason is, it's a special paper product that dissolves under high temperature water. And it dissolves basically to nothing. And there's no solid waste left other than the contamination that was on it. And there are business cases built that show that's a very cost-effective way. Southern Company uses them exclusively at all their sites. The Orex disposable protective clothing. But then you go up the road to BC Suburb, they can't build a business case for it. It makes more sense to buy and launder the cloth coveralls and hoods and stuff than it does to buy and process the Orex. So it's just a business case. So, Southern Company's dealing in volume, so it probably makes business sense to them. But use of launderable items versus disposable where it makes business sense and cost effective too. Protection of equipment from contamination by wrapping it with incinerable disposable material. I know you've seen or heard at least that things being taken into a contaminated area will oftentimes be wrapped in plastic. And the plastic will be stripped off of it prior to it being brought out of the contaminated area. As long as that plastic's incinerable, it's good. Some plastics are not. Paper products that would be used to prevent contamination should be incinerable. And this is not anything that really you on a technician level takes care of, but it's something that you need to think about, and it's something that plants are looking at, providing incinerable materials versus non-incinerable. Reason is that being incinerable, you can get a huge volume reduction. If it's not incinerable, then it's disposed of intact, and it contains, at its very best, it occupies a certain volume, which is more than what the incineration of the ashes would be from the incinerable material. All geared toward volume reduction. Here's an item. Most plants use this, and I think SRS uses it. That you have what is called a hot tool. These are commonly used tools and equipment that have become contaminated that you keep in a controlled area for reuse, rather than taking new stuff in, getting it contaminated, and then once it's contaminated, thinking, well, it's trash, so we'll throw it away. Used to be common practice, you know, crapped up, contaminated, throw it away. But now, you know, you just don't do that. As long as it's good and it's serviceable and can be used again, then maintaining a hot tool room makes sense. As far as compaction being a method, that's one method. Basically, it's just like your home trash compactor. You bale it or compress it, get a volume reduction about 3 to 7 times. There's the normal receptacle for compacting is 55-gallon DOT-approved steel barrel, 55-gallon drum. You can also compact in a B25 LSA box, low specific activity box. It's a steel box, a little bit bigger volume. There are super compactors at commercial facilities, not plants, but waste processing facilities, that can actually take a compacted steel drum or a compacted B25 and compact it. So you get that further volume reduction. You take a 55-gallon steel drum that's already got compacted waste in it, and you smash it down to about 1/3 the size that it normally was. Super compacted. As far as RP and the impact on you from compaction, there's a lot of things that you need to think about. Using a compactor, of course, as it's smashing that waste down, it's displacing air, right? And it's contaminated radioactive equipment. Even if it's low level, it's going to stir up or possibly suspend that radioactive material in the air that's being pushed out. And so that right there tells you that you need some type of ventilation. It needs to be filtered ventilation, HEPA, to take a suction on the compacting area and pull the air away and filter out the contaminants. You need to also consider that you're taking and compressing this radioactive material into a smaller space. You're increasing the specific activity. And as you increase that specific activity, you're going to increase dose rates. And so in that act of compacting, you may be actually generating a dose rate issue. And so that's why RP needs to be very involved in it, monitoring the whole process for dose rates and for airborne. Becomes a really significant factor when they're doing a super compactor, and that's usually done at a waste facility. So, but if you're an RP at a waste facility, that's something that you're going to be looking at. As I just said, we'll be increasing specific activity and increasing the exposure rate coming from the package. Now, as far as other things about compaction, there's a link here for you to go to. And I'll show you this one. Oh, there you go. This is a barrel compactor. Now this is an empty barrel, but it gives you some idea of what can be done, in case you've never seen this happen. It's nothing more than a big old hydraulic ram that goes down. Now, this is showing you how to crush in a 55-gallon drum. To actually compact material within that drum, same principle. This ram, though, would be sized so that it would go down inside the drum. Okay, you with me? It's sized so that it'll go down inside the drum. The ram will be here. And so what you would do is you would load your compactable waste in here, and then you just basically smash the air out of it. You ever notice on a drum, they've got these ridges here? Well, what you do is you smash it down, and then when the waste starts, springing back up here, you put a little poly disc in here. And you smash it. And what happens when you smash it, it kind of spreads a little bit, and it will actually lock up in this ring. And so it will lock this waste down here, and so then you put more waste on top of this, smash it further, put another ring in here, and then smash further, and then you put the lid on.
Would the heap of ventilation typically be inside that little?
Inside that box, probably
Shut
up
it.
at the top, it'd be drawing a suction on it from the top.
Okay.
As you notice, when she first closed it, she closed the door. That gives you kind of, it's not airtight. You don't want it to be airtight, but it keeps stuff from being pushed out.
Okay.
So that's a barrel compactor, and a box compactor works essentially the same way, except obviously the container would be, this is kind of a box compactor here. The box would fit in here. The ram would push the material down into the box, compressing it just as you saw in the barrel. So there's that link for you. Shows you the construction of the barrel. They are DOT certified. They have to be. That's part of the requirements for disposal of it. It's a DOT 17H 55-gallon drum. This shows another barrel compactor, specifically not to smash the barrel, but to compact the waste. You can see the ram here, and that fits down inside of that. This is a B25 box. It's a steel box. Typically, the lid just sets on top of it. If you're compacting it, it would fit into a box compactor. You compact it, and then this lid sets back down, and it has an edge. Where the lid has a lip on it. And a seal. There's a seal in there. And then there are little metal wedges that fit down in slots. You put the wedges in there, smack it with a hammer, and has a little indent so it won't come back. And basically it just wedges that lid back in place. You cannot open it back up without doing some destruction. So you don't close it until it's ready to be closed. That's the story there. It's not designed to be reopened. So that's compaction. Very effective. The plant I worked at in Arkansas, we had 2 of these, and that was one of the things the RPs did. We ran the compactor. Not just doing the radiological surveys, but actually putting the trash in it and compacting it. We later had a box compactor out at our rad waste building, and we did compact. And then, technology changes. They came up with a super compactor, and incineration came along. That was the next technology. Incineration is just what it sounds like. You burn it. This is a document, if I'm not mistaken. And, right, there it is. This is by a company called Nukem. I believe it's a German company, but they do business in the United States. I'm not going to go over this, but it has a pretty good explanation of the incineration and the process that they use. I think somewhere in here it may even have there. It has a drawing so you can kind of see what goes on during the incineration process. It's a little bit more technically involved in a trash can sitting out back, as you might expect. But you can look that over, it gives you some idea of the technology that's involved with it. Pretty high tech.
It's mostly just to prevent airborne, right? All the technology around burning it.
Yes. Well, not only to prevent airborne, but we'll talk about it, but you know, we talked about concentrating the radioactivity when you're compacting.
Yeah.
Well, this even concentrates it more because you don't necessarily burn the radioactivity. It doesn't necessarily go away. It's in that ash. So now the ash has to be taken care of, and it's usually, or it can be, pretty high dose. This is useful when we're dealing with biological waste like animal carcasses, like the radioactive bat. Can be incinerated. You get a great volume reduction. 10 to 15 times is the minimum. That's the old technology. This Nukem that I showed you there is a volume reduction of 120. So it's kind of a super incinerator, if you will. That does produce radioactive gases and particulate in addition to the solid ash residue. So all of that has to be addressed in the technology. You got to have gas cleanup, filtration systems. It can be highly radioactive, as we just said, dealing with the ash because of the concentration effect. And so you have that disposal challenge that you have to take care of. The way most of these companies work is they don't take ownership of your waste. They take possession of it, but it's your waste. They put it through their process, and they take the residue and they ship it back as your property. And then you have to take care of it, which means now you have to take care of disposal for burial. That's the way most of it works. When they first came out with it, obviously air quality standards was huge. I don't know if you remember PCPs. Does that ring a bell with anybody? Allison, you've heard of it. PCPs, it's an environmental hazard. It was a chemical that was used in transformers and but it was polycarbonate phenol or something. I can't remember what. But it was a huge environmental hazard. And anything that had PCPs in it was just, I mean, it was like double mixed hazardous waste, you know. And if you had radioactive material that had PCPs in it, that was a triple. I mean, it was nasty stuff. Nobody wanted it. Well, they came up with incineration as really the best alternative to handling PCPs. And it was through some of that technology that the radioactive incineration came about. When they developed the technology, you could safely burn off or incinerate this PCP waste. There was technology that could handle radioactive waste at the same level. And of course, the escalating cost for burial services, the shrinking land, all that stuff did drive the advancement of this technology where incineration of radioactive waste could be done economically and a lot. And I think that link is a different. Check it real quick.
Yes.
It's another Studvik. That's another major player in the waste disposal. They are, if I'm not mistaken, they're German or Swede. I'm not sure. Swedish. And but they do a lot of work in America. Any questions on incineration? Solidification, that's another process by which solids can be handled, but also liquids. Basically, you just take a batch of radioactive waste and you mix it in with concrete or some other solidifying agent, and you wind up with this chunk of radioactive material. And it will meet the stabilization. We talked about this in 10 CFR 61 as far as stabilization requirements for the burial. It does allow it to meet the stabilization requirements. It can be a variety of forms. You can see a liquid, a slurry, which is a liquid mixture of the solids. It can be sludge, like what is found out at the waste tanks out at the site. It can be dry solid. And I'm going to leave this to you to read. Basically, it just describes in general how solidification works. And this link, solidification link, I believe is another vendor. Yeah, Nukem, again, and it takes you through their process and has a simple diagram showing you how. A couple of they have 2 or 3 different methods that they use. The most common use is the cementation here, and it's just what it sounds like. It's cement. The reasons, advantages for it: simple, low temperature, proven technology. It's not combustible, has good thermal stability. It'll stand heat for extreme temperatures. It's chemically, biologically stable. And you can either mix it in with a matrix or you can encapsulate it by grout. This is a method, the grout method is what's being used to stabilize the tanks out there at the site. And the grout is nothing more than kind of a soupy cement mixture. And it's used to really to do the final step in closing out the tanks out at the site. Vitrification, we've already talked about it. I'm not going to talk about it anymore. And that pretty much finishes up the solids. As far as liquid, again, prevention is the biggest, single most effective step you can take. That's usually accomplished by segregating the clean waste from the liquid waste from the radioactive liquid waste. And you do that in plant design by having a clean waste system to process clean floor waste and equipment waste, and then a radioactive waste system to process radioactive liquid waste. There are times, though, within a radiologically controlled area where you're going to have a clean system. Circ water is a great example of that. It's cooling water. And there will be times during maintenance where that has to be drained. And what you wind up with is a tendency, if you're not careful, to drain all that clean water down into the radioactive liquid waste system. And you just created that volume of liquid waste now. So you kind of got to think, and the planning and work stages, try to help you do that. To where when you drain those clean systems, you drain them to a clean waste system so that you don't, and you try to minimize contamination and thereby reducing the volume. As far as other steps, we talked about evaporation. That was a big one, especially in the waste cleanout. Just positioning the tanks out at the site. You boil it off, concentrate it as much as you can, get it down to a solid waste, and any residual is sucked up by adding materials such as vermiculite, which is, what do you call that? Dry Ease, I think, is one of the brand names. Sawdust does the same thing, sucks up the residual liquid on a floor. What's it called? Yeah, oil to dry. Yeah. Same thing. That's what vermiculite is. It's used to suck up the residual. Demineralization, if you'll recall back in NET, that's one of the things that's used to clean up a lot of the systems to maintain purity in the rack water cleanup system, for example. And purification, reactor makeup purification system. It's used in the condensate feed. And basically, the system's liquid is passed through this mineralizer bed that has the resin in it. The resin exchanges chemicals, some of which is radioactive. It'll remove radioactivity. And in its place, it releases good chemicals. Maybe help maintain pH or conductivity or whatever. Again, ultimately, that resin will expend, and it will be spent and must be dispositioned. If it's radioactive, well, then you have radioactive resin to deal with. And we'll talk, and that radioactive resin then becomes solid waste. And solid waste can be handled through solidification. Is usually the way you handle spent resin. As far as filtration, a lot of systems have filters built into them for the purpose of removing undesirable particulates. Well, if it's a filter, it's going to remove that, right? It's going to concentrate it. So then you have that radioactivity being concentrated on the filter. The filter could be either replaceable cartridge type filters, where you take out the expended cartridge, put a clean one in, and then you've got to dispose of this contaminated radioactive filter. It may be that it's back washable, and by that it's designed so that you can basically wash. You take the filter out of service, but without opening up the system, you can do some valve lineups, and basically it washes all the collected residue off of the filter and disposes it down through hard piping to a rad waste system, and then it's processed with the rest of the liquid solid rad waste. There is technology out there that has that. There's also some advanced technology filtration, such as magnetic filtration systems. That works really good. It's a combination of magnetic as well as back washable, but it only applies if it's ferrous material. Okay, so if you have non-ferrous material, which some of the alloys that are used in the plant are, then it's not very effective. But as you can see, regardless of the design, it removes the particulate, and it is sized particulate. By that I mean the filter pore is graded by micron as far as the size of filter or size of particulate that it would remove. Regardless, that removed particulate has to be processed as radioactive waste, whether it's through the removable discarded cartridge filter or the residue from the backwash, or even the magnetic and the backwash that comes off that. Dewatering and solidification is another way of handling liquid, and we've already really discussed that. And let's see what this is. Oh, I want to show you this. We've got time. This is a little quick film clip on the closure of the last two tanks out of Savannah River. Major milestones out at the site. Let's see if it'll load and play.
It was celebrated this week at the U.S. Department of Energy Savannah River site, located in Macon, South Carolina. For the first tour since 1897, 2 years of radioactive ice storage tanks have been operational and closed. The ice tanks were the first tanks at the Savannah River site to be closed under new legislation added to the National Defense Authorization Act in 2004. The more classified the residual waste or the tanks, activities as doubled in high-level waste. The legislation was sponsored by South Carolina Senator Lizzie Graham. Because of your success, because you proved all of us right in 2004, the opportunity to have sound environmental policies and sound budget practices is alive and well. The Department of Energy Undersecretary of Homeland Security, Thomas DeLuca attended and acknowledged the accomplishment. And on behalf of the grateful nation, I say thank you for a job well done. The milestone meetings delivered 2.6 million dollars of the summer blast of burning study of South Carolina has been reduced. For South Carolina, the accomplishment is significant.
By closing these two hazardous waste storage tanks, you helped reduce the single greatest environmental risk in the state of South Carolina.
Said closure of those tanks was the latest step in a bright future for SRS.
This might be possibly more of a sign for SRS achieving the mission of success in the areas of national security, clean energy, and American stewardship.
In the eyes of civilian regulation, the EIA contractor contracted to operationally close the waste tanks, but recognized for a job well done and for operating safely. The statement on the packaging for this day, stating diligent and safe work by those employees.
78 contacts have only happened in the last couple of months. 3.34 million gallons of milk, 2,080 cement trucks, 70 workers currently involved in burning 8 hours a day, 5 days a week. And all is up to 2 closed tanks. And those that I know that I don't get excited very well, or very much, I'm excited today. I'm going to come in from 14.
So, as parent company, ORS, and contractor partners, Bechtel, CH201, and BW are welcome to the corporation.
Remember how many tanks we said there were out there?
51 total.
Yeah. So as long as there's money for the work out there to do the work, there's work to be done. Because the rest of these tanks have to be closed just like that one was. Or those two were. That gives you some idea. Now, the reason I included that there is because that final step on that is the solidification. You heard the 2,000 and something concrete trucks, over 3 million gallons of grout. That is the final step in really stabilizing it and putting those tanks out of commission and saying they're closed. But you can also use that on a much smaller scale, and it is used when we process spent resin. That spent resin is mixed in with a slurry to get it into the receptacle. Once it's there, then the liquid is processed out, it's dewatered, it's sucked out, and then the solidification agent is added, and it's mixed up and allowed to set up and harden. But that's one common method for processing spent resin, as well as the vitrification process, which we've discussed. In our last final section, we've looked at solids, we've looked at liquid, now we're going to look at gases. This one here is probably the simplest, just simply because most of it's accomplished by in-place systems. You can see the three major steps there, or possibilities, are hold-up tanks and delay lines, filtration and absorption. The hold-up tanks and delay lines are designed. The reactors you see at hold-up lines delays the release of the effluents. And what that means is you build the system so that, let's say I've got my reactor vessel, for example, and through whatever process I get my gaseous waste comes off that. And it's not a straight shot, okay, so this goes through some other processes, but let's say it's ready to go to be discharged. What they do is they actually add piping. And that's the delay lines that they're talking about. And then it would be fed into the plant exhaust stack, where whatever is remaining would be discharged out with the regular air exhaust. Now this all has rad monitoring on it and all that we talked about earlier as far as discharge. Decay tanks, oftentimes there will be a decay tank built in where it has a large capacity for maybe, I think we had like 6 decay tanks, and they were about as tall as this room, maybe a little taller than this room, and maybe 12 feet across. And they were designed to take the gaseous waste that resulted from a normal plant shutdown and hold it for as long as we wanted to hold it. And that's what we would do. We use compressors to put them in there. You know, you compress it as much as you can to get as much gas in there as you can, and you just leave it for decay. Most of the fission product gases are short-lived. Usually within, I think, 8 days, it had decayed off enough to where it could be sampled, and then it would be fed out and discharged via the effluent stack.
These lines that the gases going through at certain points, are there monitors at certain points to make sure that it is under a certain dose rate before it hits the stack? Okay.
Yeah. Yeah, they're usually it's down here. There'll be a rad monitor on the line that'll measure the radioactivity. This is all designed, the length of piping here is designed so that if I take a molecule, let's say an atom of radioactive xenon, and let's say it was born right here, it's at its max radioactivity. This is designed so that the time it takes that to travel through here and reach this point, it's decayed enough that it can be fed up in here.
And if it's not?
If it's not, then it's going to
there's
have to
a
be
shut-off
subject with a little
valve.
shut-off valve, and it'll close it off. Yeah, that is correct. The effluent is also set through filters just like it would be in a liquid system, to catch any particulate that may be entrained, because you do get, as best as you try, you're going to get some corrosion and decay, or corrosion of the piping system here that may get residual radioactivity on it, get caught up in the air, and so there will be filters installed. The tall stacks, I don't know if you look at BWR plants, that's what distinguishes a BWR from a PWR in a lot of cases, is this huge, tall stack. That is tall on purpose because it has to do with the dispersion and the decay of the gases that are a byproduct of BWR operation, along with the ley lines. But it's put into there, it gives you the good dispersion mixture as it goes up through the stack and is discharged out into the air. And you can see down here the concentration is maintained below what is required by the environmental text specs. Again, everything is geared and designed for maintaining that off-site dose as low as reasonably achievable. Filtration and absorption, we've already talked a little bit about the filtration. All of the plant ventilation will eventually go through some level of filtration prior to being exhausted into the environment. Those units that exhaust radiologically controlled areas have a combination filter and charcoal bank, and that's where the absorption comes in. The filter is there to pick up any radioactive particulate that may be entrained in the air. The charcoal banks is activated charcoal, and it is there to absorb any radioiodine that may be in the air. And these are huge banks. I mean, I'm talking about ventilation units that are the size of this room. And probably 3/4 of this room would be a charcoal bank, or a series of charcoal banks, to exhaust a place like, say, the turbine building. You'd have 2 or 3 rooms like this. What it does is it captures the radioiodine and it holds it. And usually what you do is you just basically operate it. You can and do sample and monitor the radioactivity associated with it. But typically what will happen is you can get so many cycles on a bank of activated charcoal until you have to replace it. And what they'll do is they'll shut it down at the beginning of an outage period when you shut down, and they let it decay. And toward the end of the outage period, when you're getting ready to start back up, they'll go in, do core samples of the charcoal, analyze it for radioactivity, and typically it's decayed such that it can be handled as non-radioactive. Because the half-life of iodine-131 is what?
8 days.
8 days? Yeah, a little bit more than 8 days, so, you know, it doesn't take much. And I think that captures everything that's up there. Special gases would be things like tritium or xenon, or possibly even non-radiological hazards, chemicals. But you can see, treat each one of those with specially designed ventilation. Silica gel is good for tritium water vapor. Silver zeolite is good for xenon removal. And then for chemical fumes and gases, you can do a caustic scrubber or some other absorbing material, depending on what the fumes are. And that, I believe,